Welcome back, everyone, to Flight Vehicle Dynamics. This is lecture number 5 in week 2. So today we're going to finish looking at the particle kinematics. And I remind you that kinematics describe the relationship between position vector, velocity vector, and acceleration vector. Our goal is to be able to apply Newton's laws of motion. Newton's laws of motion, especially for the translational motion, is F equals m times a, where a is the inertial acceleration. So our objective is to find an expression for the inertial acceleration of our particle p. So before finding an expression for such acceleration, let's recap a little bit what we've seen so far. So far, we've been referring to an inertial frame of reference, normally indicated with I. And then we have the body frame of reference, usually non-inertial. So sometimes I'm going to refer to it as non-inertial frame or just the body frame of reference. And I'm trying to keep also the color scheme consistent. So you'll learn to recognize also the colors. So usually with this orange, yellow, I indicate the axes or the versors of the inertial frame. And then with these maroon, purple color, I'm indicating the body frame of reference versors. Then we have the position of P. One thing that I failed to mention is that we always refer to the inertial and the non-inertial frame, or we assume that they share the same origin. If they don't, the only thing that you need to do is just to transpose one origin on top to the other. That's it. And then you can apply the rotations to switch from one frame of reference to another. Now, the position vector connects the origin of the reference frames with the particle P. And now the particle P, we have two velocities that describe the rate of distance or the rate of position of P, and that depends whether we are referring to the inertial frame of reference, so we're going to have the inertial velocity, VI, or VB, the velocity with respect to the non-inertial frame of reference. Then we have our angular velocity vector, which is the relative angular velocity of the body frame of reference with respect to the inertial frame of reference. Then we've seen the rotation matrix, which allows us to rotate from one coordinate, from one reference to another. It can be interpreted also as a change of coordinates. And then we have the Euler angles and the Euler angle rates. Now, the Euler angles and the Euler angle rates are not unique because they depend on how the rotation matrix is constructed. They depend on the sequence of rotations that you've applied. And remember, we have 12 possible sequences. Usually in flight dynamics for aircraft, we apply the 3-2-1 rotation sequence. Now, bear in mind that all the vectors can be expressed in coordinates with respect to the inertial frame of reference or the body frame of reference. So now in this table, I've summarized all these quantities expressed in both the inertial reference frame coordinates and in the body reference frame coordinates. Let's start with the easy ones. So the versors of the inertial frame of reference. Of course, these versors in the inertial frame of reference coordinates are simply 1, 0, 0, 0, 1, 0, and 0, 0, 1. whereas the expression in the non-inertial reference frame, well, that depends on the direction cosines. But once you have the versors of I expressed in the B coordinates, you can construct the rotation matrix from I to B, or RBI. Remember that we're reading things from right to left. So RBI is the rotation matrix that takes us from I to B. So we can construct such rotation matrix by simply placing these versors in the B coordinates as columns of the matrix itself. Now let's move on to describing the versors of the B reference frame. So let me start from the right here. The B1, B2, and B3 in the in B coordinates are simply the vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1. And we can say something similar when we move to the I reference frame coordinates. We can use the vectors in such coordinates to form now the RIB rotation matrix. So the rotation matrix that takes us from the body to the inertial frame of reference if we place the B vectors as columns of the matrix. And also remember that the relationship between RBI and RIB is simply that one is the transpose of the other. It is also true that one is the inverse of the other, but since these matrices are orthogonal and in particular orthonormal, so orthonormal is a special category of orthogonal matrices. Orthogonal matrices are matrices whose columns are mutually orthogonal. Orthonormal adds the fact that the norm of each column is also 1. But anyway, for orthogonal and orthonormal matrices, their inverse is equal to their transpose. So we can simply switch from RBI to RIB by taking the transpose without having to take the inverse, which is usually more of a complex operation. Now, what about the position of P? Well, the position of P, of course, can be expressed in the I coordinates or in the B coordinates, and we use the versors of either the I frame or the B frame. So here I've included all the subscripts and all the superscripts. Sometimes not all of them are going to be used. For instance, in this case, the subscript I for the I versors, if it is understood that we're talking about the coordinates in the inertial frame of reference, I usually, I'm not going to write them down, those subscripts. It's just a lot of symbols. So if it is clear, you don't have to write every time everything, but you have to make sure that it's clear. So just in this table, I'm going to write everything so that you can take this table as a reference, and then once you're confident enough and you understand everything, you can start dropping subscripts. Okay, so let's move on to describing the velocity of P. And now the velocity really depends on, and that's what we saw last time, it really depends whether it is a velocity relative to the inertial frame of reference or to the body frame of reference. So when it comes to VI, so in the I coordinates, then we have this expression here. So for details, please see the previous lecture. Whereas if we have the same vector, but we want to express it in the B coordinates, what we found last time, this very useful relationship that connects the inertial velocity with the non-inertial velocity. So VI is equal to VB plus the rotation matrix cross product the position vector. And this expression is the most used. Why? Because usually we have available VB, so the non-inertial velocity in the B coordinates, and also the position in B coordinates. And the angular velocity can be derived also fairly easily, whereas we don't really have a way most of the times to get to the inertial velocity in the inertial coordinates. That's why we prefer, or we go this route. Okay. Now, what about the non-inertial velocity? Well, we've already seen it over here, but what is that expression? Well, that is just the time derivative of the three components in the, oh, I just spotted an error. This should be B. There you go. So we have the three derivatives with respect to time of the three components of the position in the B1, B2, and B3 direction. Good that I spotted that. Of course, we can also have the non-inertial velocity in the inertial coordinates, but we never use that, so it's not really useful, and we can forget about that. Okay, then what about the angular velocity? Well, the angular velocity is the relative velocity, the rotational velocity of frame B with respect to frame I, and so being omega a vector, it also can be expressed in any coordinates, but in this case, of course, we're interested in seeing two types of coordinates, the inertial and the body coordinates. When it comes to the angular velocity in the inertial coordinates, well, once again, this is not very useful, so we're going to forget about it. What we really are focusing on, and what we found an expression for, is the angular velocity in the body frame coordinates. In other words, we found this expression here, omega of B with respect to I in the B coordinates is equal to the matrix B times this vector, which doesn't have any physical meaning, but the vector contains the Euler angle rates, psi dot, theta dot, and phi dot. And for an expression of the matrix B, I think I wrote it down later on, but you can always refer to the notes for the previous lecture. And now in the last two rows, I wrote down the expressions for the inertial and the non-inertial accelerations, but we have yet to see it. I just put it here, so in the future you can always come back to these notes and you have all the quantities already summarized, so you don't have to go back and forth. But now we're going to see how we get to the expression for the acceleration. The only thing that I'm going to anticipate is that the non-inertial acceleration in the I coordinates is not useful. The inertial acceleration in the inertial coordinates would suffice, but like the velocity is difficult to get, so we're not going to go through that route. We're still going to go through the inertial acceleration route in the B coordinates, so we're going to find a nice, a little bit longer expression for that, and in it we will see that we're going to use the non-inertial acceleration in the body coordinates, which is kind of similar to the non-inertial velocity in the body reference frame, we're just taking double derivatives of the coordinates of the position, okay? All right, so concluding with the recap of what we've seen, an expression for the rotation matrix that takes us from the inertial frame of reference to the body frame of reference is given by this expression over here. This is a particular rotation matrix that refers to the 3-to-1 rotation sequence. Let me repeat myself and saying that we have 12 possible combinations, 12 possible sequences. So possibly we can get to up to 12 expressions for this rotation matrix. And same thing can be said for the B matrix. It's not always the same. It really depends on how you construct the rotation matrix. So in this case, for the 3-to-1 sequence, I wrote down the expression, and this theta vector is simply the vector with the Euler angles. And for the 3-to-1 rotation sequence, the three Euler angles are also known as the yaw, pitch, and roll angle. For every rotation sequence, we're going to have some singularities. For the 3-to-1 rotation sequence, the singularity appears at values of plus or minus 90 degrees when it comes to the pitch angle. And so you see that usually, since we are using this transformation to describe the motion of aircrafts, aircraft usually don't fly with the pitch angle close to plus or minus 90 degrees. So we are pretty much far away from the singularity. But if you're describing the motion of fighter jets or other types of aircrafts which do fly vertically for some times, then you might have to use different rotation sequences or a combination of them, actually. Okay, then we also saw and passed the transport theorem. So let me restate it here in a better form. So this is a theorem that is valid in general. We're not going to prove it. We're just going to use the result of such theorem for the purpose of constructing. Well, we already did it for the velocity vector, but also for the inertial acceleration vector. So anyway, the transport theorem states that given two reference frames A and B with common origin O, and with the relative angular velocity omega A/B, which happens to be equal to minus omega B/A, and you can think about it. And if we pick any vector, so here, I don't want to pick, usually it's when you select a general vector, you pick the letter V, but V we're already using it for velocity, so I'm gonna use W. So let W be any vector, then the derivative with respect to time of such vector in reference frame A is equal to the derivative with respect to time of the same vector with respect to reference frame B plus the cross product between the angular relative velocity of B with respect to A and the vector itself. So of course you see that since there's no particular reason to put A before B, Then we can also write down the derivative of W with respect to time or the time derivative of W with respect to the B reference frame is equal to the time derivative of W itself with respect to A, plus now the angular velocity of A with respect to B, cross product the vector W itself. One thing to notice here that I haven't expressed the vectors, any of these vectors in any coordinates. So this is a general rule. The only reference to the coordinates that that appears is at the superscript. So it really depends on the velocity with respect to a certain frame of reference, but that doesn't mean that the vectors are expressed in the coordinates of either of the two reference frames. The vectors can be expressed in the coordinates of a third reference frame. Okay, so this is a general statement. All right, so let's now find the expression for the inertial acceleration of P, and then we're going to see a couple of applications of this stuff. All right, starting with the position, I don't need to repeat that, we saw it, and so we also saw the inertial velocity expression of P. Now here I've dropped the subscript just because it's going to be easier to read, but I'm referring to the B reference frame in terms of coordinates. But the expression is valid in general with respect to any coordinates. So, but usually we have the expressions of these vectors in the B coordinates. So we're going with that. Anyway, now we have that the inertial acceleration is the time derivative of the inertial velocity with respect to the inertial frame of reference. So now let's apply right away the transport theorem. So the transport theorem says that the time derivative of a vector with respect to I, so go back and just substitute I with A here. So that is equal to the time derivative of the same vector with respect to reference frame B plus the angular velocity, the relative angular velocity between the two frames of reference, cross product the vector, which in this case is the inertial velocity VI. Now in the next step, I'm going to substitute the expression for the inertial velocity vector as a function of the non-inertial velocity VB and the angular velocity and the position vector once again. So now we have the time derivative with respect to B of VB plus omega cross product R plus omega cross product. Now, once again, the expression of the inertial velocity, which is the non-inertial velocity VB plus omega cross product R. Now here I've dropped another thing, which is the superscript B relative to I, but it is understood that when we're talking about this angular velocity, we're really talking about this angular velocity, omega B slash I. All right, so taking the derivative of term by term, we find dVB over dt, which is the non-inertial acceleration, whose expression is over here, okay? Then we have the time derivative of the cross product omega and R, cross R. then we have a omega cross VB plus omega cross product R. So finally, we see that once we work out all the products, that the inertial acceleration AI is given by the non-inertial acceleration plus 3 extra terms. So we're going to have 2 omega cross product non-inertial velocity VB, which is also known as the Coriolis acceleration. And I'm sure you've already heard of it, but I don't know if you've ever gotten to the Coriolis acceleration this way, but now this is, in my opinion, the most proper way of getting to all these terms. So it's really, with all these superscripts and subscripts, you keep track of what you're doing. Then we have another term which contains the derivative of the angular the angular velocity, which is indeed the angular acceleration. And then we have this double cross product, which represent the centrifugal acceleration, sometimes also known as the transport acceleration. Notice that once again, for these vectors, I'm not expressing the coordinates, but in practice, we usually refer to all these vectors expressed in the body reference frame coordinates, as pointed out in our useful table over here. But just a reminder, please always double check what I write and try to rederive everything that I do. So in case I made a mistake somewhere, you're gonna catch it. Okay, so this concludes actually the particle kinematics. So let's take a look at an example. In particular, we're starting with something simpler, so it's just a two-dimensional motion. So we're gonna have our particle P, which is traveling along its path, whatever that is, and here it's just this black line over here. So the body frame of reference is normally centered on the particle itself. That's why I have the two axes B1 and B2 centered on P. And we have also the inertial frame of reference I1 and I2, but now this frame of reference is centered at point O. So you see that the two reference frames do not share a common origin. So what do? Well, we just move the body reference frame from P to O so that they share the same origin. So our new non-inertial body frame of reference will have an origin also at O, so it will be O, B1, B2, and B3. The body frame of reference rotates with respect to the inertial frame of reference, and so if we want P to travel just in the plane of the page, then the angular velocity is perpendicular to the page at all times. So let's start constructing the vectors that we've seen, starting with the position of P. So position of P in the body reference frame, well, it's simply R in the B1 direction. And once again, here, we are referring to the body frame of reference centered in O. So even if it's centered somewhere else, what you do is just you shift it. because in the original body frame, well, the position of P relative to the original B centered in P would be simply 0. But now, once we transpose the body frame of reference to the origin O, now the position of P with respect to O is R. In which direction? Well, in direction B1. So now let's take the first step and compute the non-inertial velocity of P. Well, the non-inertial velocity is VB in the B coordinates. It's just the time derivative of the components. So here we only have R dot, always in the B1 direction. Since the components in the B2 and in the B3 directions are 0, then also their derivatives with respect to times are 0. So the non-inertial velocity of P in B coordinates is given by R dot 0, 0. What about the inertial velocity? Well, the inertial velocity, we have our useful formula that relates the non-inertial velocity with the angular velocity of the frame of reference B with respect to I and the position vector. So now we have to come up with the angular velocity of frame of reference B with respect to I. So it is quite intuitive to see that such vector is 0, 0, psi dot. But if we are not convinced about that, let's just construct it the way we would do it normally. So let's see, how many rotations do we need to perform to go from the inertial frame of reference to the body frame of reference? Well, there's just one rotation about the z-axis, counterclockwise, so the angle is positive, and that's it. So it's just one elementary rotation about the z-axis. So RBI, so the rotation matrix that takes us from I to B, is simply R3 of psi. The other two angles are 0 and also their derivatives. So our overall rotation matrix is simply given by the elementary rotation about axis 3. And consequently, we can find the matrix B, which is very simply 0, 0, 1, 0, 1, 0, and 1, 0, 0. And so by multiplying B with the vector containing the other angle rates, in this case only psi dot, because theta dot and phi dot are 0, we indeed find that the angular velocity of B with respect to I is simply the vector 0, 0, psi dot. So it was kind of obvious in this case because the rotation is only about the z-axis since P remains in the plane of the page. But this is how you construct it in general. All right, so now let's apply, let's actually do our calculations. So I'm gonna skip naming the steps so you can check them for yourselves. And we find that the inertial velocity in B coordinates is given, it has two components, one component in the B direction given by R dot and a component in the B2 versor given by psi dot times R. Now we're ready to express or to find the expression for the inertial acceleration of P. So here is just a little bit longer, but we have everything that we need. We know all the vectors. The only one that we haven't really found is the acceleration, the non-inertial acceleration in B coordinates, but that is simply given by the second derivative with respect to time of the coordinates, the position coordinates. So since the position vector is r00, then AB in the B coordinates is r double dot 0, 0. So this is really the easiest part of this expression. Well, the other vector actually that we haven't mentioned is the derivative with respect to time of the angular velocity. In this case, the angular velocity is very easy, 0, 0 psi dot. So its time derivative is 0, 0 psi double dot. We know everything else, so you can compute all the cross products, and I invite you to review your math skills, because, you know, they might be tricky, especially taking care of the sign appropriately. All right, so in the end, we find that the inertial expression for the acceleration of p in the b coordinates has two components, one in the b1 direction given by r double dot minus psi dot squared times r, and the component in the b2 direction, which is 2 psi dot r dot plus c double dot and r. Now we could simplify this expression in the assumption that, for example, the body reference frame rotates at a fixed angular speed with respect to the inertial frame of reference. So if omega was constant, then this would mean that omega double dot would be 0, or in other terms, you wouldn't have this term over here, which in the end, you see, it's like putting psi double dot equals 0. All right, before seeing another example, but just briefly, because I want you to work on it on your homework, but I've done all the calculations for you, but I'm just going to describe the problem, and then I want you guys to try and figure it out, or to interpret what I wrote. It should be pretty clear. But anyway, before doing that, I want to make you understand a little bit better why the derivative of versors is given by, so we saw last time that the derivative of B is given by the angular velocity cross product, the vector itself. So let's take a look at why that is the case. Again, this is not a proof, it's just a two-dimensional case, which will then be expanded to 3D with a little bit of faith. But nevertheless, I just want you guys to understand where it comes from. Okay, so let's take a look at this frame of reference, E1, E2, and E3. And let's assume that this frame of reference is rotating. So it's not an inertial frame of reference. It is rotating about its E3 axis. So E3 is fixed, whereas E1 and E2 are not. And the angular velocity is just omega in the E3 direction. Now, E1, E2, and E3 are taken at first at time t, and then we'll let some infinitesimal amount of time pass, so dt, and let's see where the position of these vectors change. So E1 at time t plus dt, and E2 at time t plus dt are. All right, so the difference vector-wise between E2 at time t plus dt and E2 at times t, and of E1 at time t plus dt and at time t are given by a minus sine of omega dt times E1t. So minus sine of omega dt because it's just the angle. The angle that E2 sweeps is just omega is constant, times dt. But now I can approximate this sine with its argument because the angle itself is very small. It tends to zero, as a matter of fact, because dt tends to zero. It's an infinitesimal amount of time, and therefore the angle is also infinitesimal. So omega dt also tends to zero. Therefore, I can approximate the sine of omega dt with omega dt itself. So we have that the difference between the E2 versor at two different times is given by minus omega dt times E1 ET. Why times E1 ET? Because it's simply in the E1 direction at time t. Similarly, we can find an expression for the difference between the two E1 versors, and that is given by, with the approximation of valid for small angles, of omega dt in the E2 direction. Now, if we take the difference between these two vectors and we divide everything by dt, well, we have the time derivative of such vectors, which are equal to omega E2 and minus omega E1, which you can express also dE1 over dt as omega cross product E1 itself, and same thing for E2. So now the leap of faith is going from this case to a more general case, and so don't worry about the proof. If you're interested about the proof, well, we can talk about it privately, but when it comes to this class, I'm fine with you just understanding where this thing comes from, but I'm not really interested in you knowing the mathematical proof. Also because there's not really one, so you shouldn't worry. But anyway, what I want you to know is that this applies for any vector. So the derivative of a vector that changes with time is equal to the angular velocity cross product the vector itself. Of course, if the vector is time invariant, then it wouldn't change. We wouldn't have a angular velocity, so its derivative with respect to time would just be zero. But if these vectors are changing, if in this case these versors are changing their direction, well, their time derivative is given by the angular velocity cross product the vectors themselves. So now the last thing that I want to see is another example. So don't be intimidated by this, but let's try to understand it together. So the example here, this is actually very useful when it comes to orbital mechanics, and when we describe motions of satellites or even of regular airplanes, but with respect to the ECI, so the Earth-centered inertial frame of reference. All right, so now let's see our setup. We have the inertial frame of reference, as usual, indicated with the orange colors, or orange yellow colors. And if you go back to a previous lecture, now I don't remember if it was lecture 2 or 3, but we defined all the reference frames And this is the ECI, so the x-axis points towards spring equinox, and it's fixed in space. Then we have the I3 versors that points through the North Pole, and I2 completes the frame and lies on the equatorial plane. So you can see, you can think about this as the Earth with the equator, and then we have the Greenwich meridian. And then we have our vehicle, P. So we have its position with respect to the center of the Earth is given by, well, RE, which is the Earth radius, and it's a constant. And then we have a non-constant altitude, H. And so we can define a body frame of reference. Well, technically, the body frame of reference would be centered at P, but we use the topological frame of reference, so it's centered at the projection of P on the Earth's surface. So the origin is S, and we have B1, B2, and B3 constructed so that B1 points towards the zenith, B2 points towards the local east, and B3 points towards the local north. How do you find the directions of the local east and the local north? Well, you have to follow tangentially the local parallel and the local meridian, respectively. Now we know that this non-inertial frame of reference, B subscript S, and I'm using subscript S because I'm referring to it as centered in the S point. We need to transport it so that its origin coincides with the inertial frame of reference. So our new body frame of reference is going to be B centered at O, but the direction of B1 and B2 and B3 are the same. Okay, I haven't drawn them on starting at O, just because otherwise it would have been too cluttered. We can also define two intermediate frames of reference. I2 is just, it's not really important to visualize where it is. It's just an intermediate frame of reference, whereas I1 can be thought physically as the frame of reference that rotates with the Earth. So it's the rotating, go back to lecture 2 and you'll see which one I'm talking about. So it's still centered in the center of the Earth, and it shares the same Z or I3 axis, I3 equal to I3 prime axis with the Earth fixed, but it rotates with the Earth. So it's fixed with the Earth. It rotates with the same angular speed of the Earth itself about its axis. Okay, so I am going to stop here, and I want you to go through this. So what I've done is, of course, the goal is to express the acceleration of the particle P in terms of, well, the inertial acceleration of the particle P in the B coordinates. So we're doing exactly the same thing that we've done for the previous case, but it's a little bit more complicated. The only thing that I want to point out is that how we go from the inertial frame of reference I to the body frame of reference in terms of rotation. So we first go from I to I prime by performing a rotation of this angle theta g, which is also known as the Greenwich sidereal time. It's, yes, it is a time, but it's geometrically speaking, it's actually an angle. But of course, you can express an angle in terms of time. The Earth rotates 360 degrees in 24 hours. So you can express an angle in terms of time. So that's why it's called sidereal time. So that's the first transformation. The first rotation is about the z-axis of this angle theta g. Then in order to go to I2, we perform another rotation of the angle lambda, which is the longitude, actually, of the local longitude of our vehicle P. But you notice here that theta g and lambda are rotations about the same axis. So actually, they do not constitute independent rotations. So you can also go directly from I to I double prime by performing a rotation R3, of which quantity of the sum of theta g and lambda. Is this a counterclockwise or a clockwise rotation? Well, you see that the rotation about the z-axis is counterclockwise, so the angle is positive. Now, how do we get from I2, so from here to RB1? Well, we have to perform a rotation of the angle phi, which is the latitude of our vehicle. But now the rotation has to happen about the local y-axis or second axis. And now the rotation happens clockwise. So the clockwise rotation means negative rotation. So it's R2 of minus phi. So that's how we get from the inertial frame of reference to the body frame of reference. You can think about it as 3 rotations, so 3, 3, 2, but since 2 of them are not independent, it's also equivalent of having 2 rotations just about 3, the z-axis and then the y-axis of theta g plus lambda and minus phi angles respectively. So yeah, you can construct all the rotation matrices between each of these reference frames and use them to find the expression for the angular velocity. And if you follow the notes from last lecture, you should be able to follow and to find the same expression. Then we find the inertial velocity, and finally the inertial acceleration. So you see that here the calculations are a little bit more lengthy, but I would like you to redo it, also in case I made some mistakes or I put some mistakes purposely on it. You'll never know unless you do it. But anyway, here's a recap of, for this specific case, of the position, the inertial velocity, and the inertial acceleration of a particle, P, it can be a satellite or an aircraft, in the non-inertial body coordinates. All right, so this is all for me for this week. I'm gonna see you virtually next Wednesday because Monday is Labor's Day. So have a nice weekend and take care.